Good day, everyone. At this stage, we're now going to continue with our discussion with surface and solids. This time, we're going to discuss cylinders and cones. Let's start with cylinders. Consider the solids in figure 9.26, in which congruent circles lie in parallel planes. Plane 1 and plane 2, in which circle lie on parallel planes. For the circle on the left, centers O and O prime, O and O prime are joined to form the segment OO prime. Similarly, Q, Q prime, the centers of the circles on the right. Let the segments such as XX prime join 2 points of the circle on the left so that XX prime is parallel to OO prime. If all such parallel segments such that XX prime, YY prime, and ZZ prime are drawn, then a cylinder is generated. Because OO prime is not perpendicular to the planes P and P prime, the solid on the left is an oblique circular cylinder. With QQ prime perpendicular to the planes P and P prime, the solid on the right is a right circular cylinder. For both cylinders, the distance h between the planes P and P prime is the length of the altitude of the cylinder. H is also called the height of the cylinder. The congruent circles are known as the bases of each cylinder. A right circular cylinder is shown in the figure 9.27. However, the parallel planes are not pictured. So here, we can have plane 1 and plane 2. You have the two bases, which are circles, and you have the altitude, which is your height. The line segment joining the centers of the two circular bases is known as the axis of the cylinder. For a right circular cylinder, it is necessary that the axis be perpendicular to the planes of the circular bases. In such a case, the length of the altitude h is the length of the axis. Let's have the surface area of a cylinder. The formula for the lateral area of a right circular cylinder found in the following theorem should be compared to the formula lateral area L is equal to the height h times the perimeter. The lateral area of a right prism whose base has a perimeter P. In theorem 9.3.1, the lateral area L of a right circular cylinder with altitude of length h and circumference c of the base is given by L equal to h times c. The alternative form, lateral area of a circular cylinder, can be expressed in the form L equal to 2 pi r h, where r is the length of the radius of the circular base. For Theorem 9.3.2, the total area T of a right circular cylinder with base area B and lateral area L is given by T equal to L plus 2B. Considering circular bases, where R is the length of the radius of the base and H the length of the altitude of the cylinder, the total area can be expressed in the form T equal to 2 pi R times H plus twice of pi R squared. For the right circular cylinder shown, find the exact lateral area L. Find the exact surface area T. From the figure, R is 5 and H is 12. Take note that R is 5 and H is 12, both in inches. From the formula, the lateral area is 2 pi R times H. So 2 pi times 5 times 12. So that would give us 120 pi square inches. For the total surface area, it would be the lateral area L plus twice of the base area. So it would be 120 pi plus 2 pi r squared. So twice of pi times r squared. It would be giving us 120 pi plus 50 pi, a total of 170 pi square inches. Let us now consider the volume of a cylinder. The volume of a cylinder follows area of the base times the height. In considering the volume of a right circular cylinder, recall that the volume of a prism is given by capital V equal to the base area B times H. In figure 9.28, we inscribe a prism in the cylinder as shown. Suppose that the prism is irregular and that the number of sides in the inscribed polygon increases without limit. Thus, the base approaches a circle in this limiting process. The area of the polygonal base also approaches the area of the circle. That is, the base area is approaching a circular area pi r squared. As a result, the volume of a right circular cylinder As a result, the volume of the prism approaches that of a right circular cylinder. Our conclusion is stated without proof in the following theorem. The volume V of a right circular cylinder with base areas B and altitude of length H is given by capital V is equal to capital B times H. In the alternative form, where R is the length of the radius of the base, the volume for the right circular cylinder can be written as V equal to pi r squared H. If the diameter is 4 centimeters and the height H is equal to 3.5 centimeters, use a calculator to find the approximate volume of the right circular cylinder shown in the figure 9.29. Give the answer correct to two decimal places. So take note that the diameter is 4 centimeters. We can also say that the radius is 2 centimeters with a height 3.5 centimeters. So diameter is 4, so it follows R is 2. The volume is given by pi r squared h. Volume, pi r squared h. So that would be pi times 2 squared times 3.5. So that would be 14 pi, approximately equal to 43.98 cubic centimeters. Table 9.2 should help us recall and compare the area and volume formulas. For prism, the lateral area is h, or height times perimeter. For cylinder, it would be lateral area equal to height times the circumference. The total area for both prism and cylinder would be lateral area plus twice of the base area, while the volume is the area of the base capital B and multiplied to the height h. Now let us consider cones. Cones would be related or something parallel in its definition to pyramids. In figure 9.30, point P lies outside the plane containing the circle O. A surface known as a cone results when line segments are drawn from point P to all points on the circle. However, if P is joined to all points on the circle as well as to the points in the interior of the circle, a solid is formed. If the segment PO is not perpendicular to the plane of circle O in figure 9.30, the cone is an oblique circular cone. In figure 9.30 and 9.31, point P is the vertex or the apex of the cone, and circle O is its base. The segment PO, which joins the vertex to the center of the circular base, is the axis of the cone. So this would serve as the axis of the cones. And this would be the base, while this would be the apex or the vertex of the cone. If the axis is perpendicular to the plane containing the base, as in figure 9.31, the cone is a right circular cone. In any cone, the perpendicular segment from the vertex to the plane of the base is the altitude of the cone. In a right circular cone, the length h of the altitude equals the length of the axis. So this is perpendicular, making it a right circular cone, and the height of this cone is the length of the axis of the cone. Oblique cones would also have heights, but it is not the same as the axis or the length of the axis of the cone. For right circular cone, the own and only for this type of cone, any line segment that joins the vertex to a point on the circle is a slant height of the cone. We will denote the length of the slant height by L as shown in figure 9.31. So this is your slant height. Slant height. Now let's have the surface area of a cone. We know that the lateral area for a regular pyramid is given by lateral area is equal to 1/2 the slant height times P or the perimeter. For a right circular cone, consider an inscribed regular pyramid as in figure 9.32 below. If we're going to have the limit of the polygon as the number of side approach infinity, we're going to have the limiting process similar to what we have done in cones, in prisms and cylinders. As the number of sides of the inscribed polygon's base grows larger, the perimeter of the inscribed polygon approaches the circumference of the circle as a limit. In addition, the slant height of the congruent triangular faces approaches that of the slant height of the cone. Thus, the lateral area of the right circular cone can be compared to L equal to 1/2 of the slant height L times the perimeter P. For the cone, we have lateral surface area L is equal to 1/2 of the slant height L times the circumference of the base C. The fact that C is equal to 2 pi r leads us to the formula lateral area L is equal to pi RL. In theorem 9.3.4, the lateral area L of a right circular cone with slant height of length L and circumference C of the base is given by capital L equal to 1/2 of slant height L times C, and in its alternative form, where R is the length of the radius of base capital L, it would be equal to pi RL. The following theorem follows easily from theorem 9.3.4 and is given without proof. For theorem 9.3.5, the total area capital T of a right circular cone with base area capital B and lateral area capital L is given by total surface area equal to one base area plus the lateral area. If we are considering circular bases, where R is the length of the radius of the base and L is the length of the slant height, so T is equal to area of the base pi r squared plus lateral area pi RL. For the right circular cone with radius r equal to 3 centimeters and h 6 centimeters, find the exact and approximate lateral area L and B exact and approximate total area T. So take note that the radius is 3 and the height 6. So for perimeters or for lateral surface area, we would be needing the slant height L. So we have L squared is equal to R squared plus H squared. So we need the length of the slant height L for each problem part. So we apply the Pythagorean theorem. L squared is equal to R squared plus H squared. With a given radius 3 and the height 6, We plug it into the formula and we have 9 plus 36 equal to 45. Evaluating the slant height L, we would be having square root of 45, which is 3 square root of 5. Using L, or the lateral area, equal to pi RL, we have L is equal to pi times 3 square root of 5. So the exact value is 9 pi square root of 5 square centimeters, while approximately it is equivalent to 63.22 square centimeters. We can also compute for the total surface area equal to the area of one base plus the lateral area. So that would be pi r squared plus pi rl. So the total surface area is equal to pi. We plug in r is equal to 3. So that would be 3 squared. And then we have pi rl. So pi times the radius is 3. And the slant height is 3 square root of 5. So the total surface area is equal to 9 pi times the quantity 1 plus square root of 5 square centimeters, while approximately it is equal to 91.5 square centimeters. The following theorem was illustrated in the solution of example 4. In a right circular cone, the lengths of the radius r of the base and the altitude h and the slant height l satisfies the Pythagorean theorem, that is L squared is equal to r squared plus h squared in every right circular cone. So this does not apply for oblique triangles or oblique cones. For the volume of a cone, we know that the volume of a pyramid is given by the formula V is equal to 1/3 of base times the height. Consider a regular pyramid inscribed in a right circular cone. If its number of sides increases indefinitely, the volume of the pyramid approaches that of the right circular cone. See the figure below. Then the volume of the right circular cone is equal to V, which is equal to 1/3 of base times height. Because the area of the base of the cone is base equal to pi r squared, an alternative formula for the volume of the cone is given by capital V equal to 1/3 of pi r squared times h. We state this result as a theorem. So the volume V of a right circular cone with a base area B and an altitude of length h is given by capital V is equal to 1/3 of base times height. In its alternative form, where r is the length of the radius of the base and the formula for the volume of the cone is usually written as V equal to 1/3 pi r squared h. Table 9.3 should help us to recall and compare the area of the volume formulas. For pyramid, the lateral area is 1/2 slant height times the perimeter, and for the cone, the length is 1/2 slant height times the circumference. So the equivalence of perimeter to cone is being considered. The formula for the total surface area equal to one base area plus one slant or one lateral area is the same. And the volume 1/3 of the base area times the height is also the same. For pyramid, the slant height L is the square root of a squared plus h squared, where a is the apothem and h the height. For the lateral surface, the slant height L, it would be equal to r squared plus h squared for cones. Now let us consider solids of revolution. Suppose that part of the boundary for a plane region is a line segment. When the plane region is revolved about this line segment, the locus of points generated in space is called a solid of revolution. The complete 360-degree rotation moves the region about the edge until the region returns to its original position. The side or the edge used is called the axis of the resulting solid of revolution. Let us describe the solid of revolution that results when a rectangular region with dimension 2 feet by 5 feet is revolved about the 5 feet side as shown in the figure 9.35a. So what happens is we rotate it about the 5-inch side. So we are going to have this being rotated to this axis. So we are going to have a cylinder. If a semicircular region with radius of length 3 is revolved about the diameter shown in figure 9.35b. So that would be resulting into a sphere. In figure 9.35a, the rectangle on the left is revolved about the 5 feet side to form the solid on the right. The solid of revolution generated is a right circular cylinder that has a base radius of 2 and an altitude measuring 5 feet. In figure 9.35b, the semicircle of on the left is revolved about its diameter to form the solid on the right. The solid of revolution generated is a sphere with radius of length 3 centimeters. It may come as a surprise that the formulas that are used to calculate the volume of an oblique circular cylinder and a right circular cylinder are identical. To see why the formula V equal to base times height or V equal to pi r squared can be used to calculate the volume of an oblique circular cylinder. Consider the stacks of pancakes as shown in figure 9.37a and 9.37b. So it just looks like the pancakes are pushed on one end, and that would make it an oblique circular cylinder. With each stack h units high, the volume is the same regardless of whether the stack is vertical or right versus oblique. It is also true that the formula for the volume of an oblique circular cone is the same as the formula for the volume of the right circular cone. For both the right circular cone and oblique circular cone, the volume is one-third the base area times the height, or V is equal to pi